Hi class, welcome back to Electromagnetics. We're going to wrap up the section 5 here, the course, where we're continuing to look at how electromagnetic waves propagate when going through mediums that are other than free air or in combination with other mediums. So that's what we'll look today and how it affects the waves with reflection and transmission. We'll do a quick historical background, again looking at people that in the past that have influenced the study of electromagnetics. This is one you'll probably know. Education, University of Cambridge and Trinity College. This gentleman worked and was the author of the work Principia, which formulates the laws of motion and gravity. That should be a dead giveaway right there. Of course, here's the image, even more of a giveaway, pretty recognizable character. And of course, this is Isaac Newton. Lived in 1642 to 1726. Some of the notable things, he shares credit for the development of calculus. Most people, our historians, feel that he probably did it first, and then if you read the history of it, he kind of gave hints of it and how it works to his colleague. I can't remember if it was Leibniz or L'Hopital now, I can't remember, but whoever it was, they ended up getting credit for calculus because they developed the notation that we use. Isaac Newton used a different notation. He did major work in optics, which led to later understandings in electromagnetics, so he was a huge contributor in many different ways in that way. One interesting fact about him is while considered a Christian, he did have serious doubts about the Trinity. Most people feel from his writings that he didn't accept the theory or the explanation of the Trinity. He definitely explored prophecy and especially Revelations. He was obsessed with that. With extensive study of the book of Daniel and of Revelations, he calculated an end year according to Scripture, adding things up and seeing how things fit together. And interestingly enough, he originally came up with the year 2060. And so for a long time, this is what people accepted as his calculation for that. One thing that's a little concerning now is that when many people went back and re-examined his calculations, they claimed he had an error in his calculations. And he did these based on generations, so generational error. And of course, biblically speaking, a generation is usually considered to be 40 years. So if you back that error out, guess what? You guessed it. It adjusts now to the year 2020. Kind of interesting in light of some things going on right now. He went back and recalculated a couple of times, kind of based on different things and doing it different ways. So the other version he came up with was 2034. So I don't know about you, but I don't know, it's interesting. I'd love to see those calculations and how he formulated that. If you'd like to read more about that, here's a quick link that I found that I thought was pretty interesting, but I'm sure there's others out there as well. So again, we're going to wrap up part 5. We've looked at how electromagnetic waves behave with mediums other than air, or free space, I should say. And so we've looked at there's 3 types: conductors, dielectrics, and magnetic materials. We went back and resolved Maxwell's equations using the wave equation and got mathematical representations of that. Then we looked at uniform plane waves and dielectrics and conductors and some of the special properties there. We looked at boundary conditions. If you go from one material to another, what exactly happens according to Maxwell's equations, and we're going to extend that today to quantify or give some framework for reflection and transmission. So with our new boundary conditions defined, we see how different components are related at boundaries. But what about other components? Remember, like the electric wave, the electric field vector intensity, the tangential components are always equal at the boundary, but the normal ones aren't. And we have a way to roundabout get to that, but we have to take that in consideration, what's going on there. So one thing we have to keep in mind is we still have to operate within the law of energy conservation. That is, energy has to be conserved. It can't be destroyed. It can't be erased. We can't just say it goes away. So we will see that at the boundary, some parts of each component may be transmitted into the new medium, while other parts of each component may be reflected back into the original medium. All in all, the total sum has to stay the same. So we're going to take a look at this phenomenon and then how we characterize that mathematically. So to begin with our examination, we're first going to consider a boundary of two mediums with differently defined characteristics as shown below. So we have medium 1, and we see that it has a conductivity, a permittivity, and a permeability. So this accounts for the conduction, polarization, and magnetization of electromagnetic waves in this medium. And then medium 2, same thing, it has its own conductivity, permittivity, and permeability. And so we'll consider at least they could be different, and we're going to assume for this case that they are all different. Then we're also going to define some directions. So we're going to say that the wave is propagating in the plus z direction. So it's coming from left to right. And then as it continues into this medium, that'll continue in the plus direction. And so naturally going back against the z-axis toward the origin will be the negative direction. All right, and we're saying the boundary is located at z equals 0. So at this boundary, we can now characterize the transmitted and reflective electromagnetic waves, wave components in medium 1 as follows. So we can say then that this electromagnetic wave, or at least the E field, the electric field, as it travels along the z-axis, we're going to have a plus component, and so that's what's being transmitted or going to the right. And then we will have the second component, E minus, which is going to be the part of the field that's reflected and going back in the opposite direction. Add them together, that should give us the total field that we were started with, right? And so we have our propagation constant here that we talked about and defined earlier to help us characterize how the wave is going to propagate. Likewise, magnetic field, exact same thing, except this time it's in the y direction, and so again we'll have transmitted and reflected portions of the original wave. And we can rewrite that in terms of the electric field by using this intrinsic impedance. We've seen that with the constitutive relationships. So now we have everything in terms of the electric field. Again, here's the propagation constant we defined earlier, and this is basically just a function of our permittivity, permeability, and wavelength and conductivity. So these are all physical properties of the medium that we're in, except for the frequency, of course, which is attributed to the source. And our intrinsic impedance. Also, these are all just the characteristics of the medium: conductivity, permittivity, permeability, and then also frequency dependent. So again, that's attributed to the source. Likewise, we can do this in the second medium. So in this medium, we're only dealing with transmitted wave, right? And there's nothing to be reflected at the boundary into the new. It's always just reflected back. So here we only have the E field moving in the right direction, or to the right, excuse me, positive Z direction. Likewise with the magnetic field, same thing, only transmitted, no reflected. Now if there was another boundary, we could have a second reflection, and we might actually look at some of those cases later in the course. So again, we can write this in terms of just the electric field with the intrinsic impedance is what relates the electric and magnetic fields. And again, we have this propagation constant, again defined for our medium number 2, where you can see all the parameters have subscripts of 2. The frequency stays the same as it's dependent on the source. Same thing with the intrinsic impedance. Again, just a function of the material and the source frequency. So now if we come back to our boundary, we now enforce the boundary condition constraints that we've learned last time on these new definitions of our electric and magnetic fields. And we see that EX1 has got to equal to the electric field in the second medium at z equals 0, or at the boundary, because those are parallel to the boundary, tangential. And then our magnetic fields, same thing, at the boundary, those have to be equal. So applying these conditions to the previous equations, we will see then that the transmitted wave plus the reflected wave has got to equal to, in the first medium, has got to equal to the transmitting wave in the second medium. And then likewise for the magnetic, remember that we can substitute with E fields if we use the intrinsic impedances. And so this says, or tells us then, that the transmitted wave minus the reflected wave divided by this intrinsic impedance has got to equal to the transmitted wave over here divided by its intrinsic impedance. And so we see here these intrinsic impedances are what's going to help us define how much of the wave actually makes it through the boundary and is transmitted. So now we can use the above relationships to define a ratio of the reflected wave and the transmitted wave at the boundary. And so what that looks like then is, if we take the reflected wave divided by the transmitted wave, if we were to plug all these in, we would see it reduced to just the intrinsic impedance of the second medium minus the first over the sum of the two intrinsic impedances, which incidentally, this will also give us the negative of the reflected magnetic wave over the transmitted magnetic wave. And so this is a new definition here. This is our reflection coefficient, which we will use for different aspects through the course. So again, this is the reflection coefficient at that boundary. So at each boundary we define a new reflection coefficient, which will give us some information about how the wave is going to behave as it goes across that boundary. We can also use these above relationships to define a ratio of the transmitted waves at the boundary as follows. And so this is signified by a lowercase tau, previous was capital Tau. And so we have our transmitted wave plus our reflected wave divided by just the transmitted part of the wave. And so what we would find out is this is basically equal to 1 minus the reflection coefficient. So this is known as our transmission coefficient at the boundary. So whereas the reflection coefficient gives us some indication of what happens to the wave as far as what's reflected, this gives us indication of what happens as far as what's transmitted. And so again, important coefficient, transmission coefficient. So let's look at some observations then. When the two intrinsic impedances are equal and we plug them into those values, we'll get a reflection coefficient that's equal to 0 and a transmission coefficient that's equal to 1. So when this occurs, it's considered a matched condition, and the incident wave is transmitted entirely into medium 2, and hopefully that makes sense. Should be pretty obvious. So when our conductivities are equal to 0 on both sides, that is, they are both perfect dielectrics, then the intrinsic impedances are both real. Therefore, our reflected coefficient and our transmission coefficient are both real. Assuming the permeability are equal, then there is no magnetization effects. We're not dealing with any magnetic materials. Assuming that, then we can rewrite our reflection coefficients and our transmission coefficients in terms of just the permittivities of each material. So the permittivity of medium 1, permittivity in medium 2. So we plug those in, we can get them both. That's if we're dealing with perfect dielectrics on both sides. So when the second medium is a perfect conductor, that is, the sigma 2, or conductivity in medium 2, is infinite, then the intrinsic impedance of that second medium is equal to 0. And the reflection coefficient is then equal to -1, and our transmission coefficient is equal to 0. This means medium 2 is a perfect conductor and the incident wave is entirely reflected, since there can be no time-varying fields inside a perfect conductor. This would create a standing wave, which we're going to look at in a little more detail a little later. So again, perfect conductor, it's not going to accept any of the waves, so it'll reflect it all back. Let's look at a quick example. Looking here at region 1, which we're going to say for z less than 0 is free space, whereas region 2, which after we cross the z equals 0 boundary, is a material medium characterized by the following. So we're going to have this conductivity of 10 to the minus 4. We're going to say that the permittivity is 5 times that of free space, and we're going to say that there is no magnetic phenomena going on here, as the permeability is just equal to the permeability of free space. So for a uniform plane wave, having electric field defined by this, it's just a trigonometric function, and it's going to be incident on the surface at z equals 0 from region 1, so from free space. What are the expressions for the reflected and transmitted wave electric and magnetic fields? So can we use these tools that we've just learned to determine what that is? So substituting the above values for region 2 into our equations, we're going to have that our propagation constant then is 6.283 plus J 9.425, that's 10 to the minus 3. And our intrinsic impedance then is this magnitude with this angle. So remember, since they're not perfect dielectrics, the intrinsic impedance is not all real, so some of it's imaginary, and we'll look at that later. That's going to introduce phase shifts. That's what this is telling us. So we also note that eta 1 is equal to the intrinsic impedance of free space. So the intrinsic impedance in region 1 is just that of free space. So with all this in hand, we're going to do some calculations. So our reflection coefficient then, we will put in the value of eta 2 that we just came up with, and eta 0 we calculated early in the course is 377 ohms. So we plug all these values in, we do the complex math, and we come up with this new value here, which is our reflection coefficient. Likewise, we can calculate our transmission coefficient, just say 1 plus this value, and when we do, we come up with this result here. So again, just rewriting that. So finally, we're going to have that our reflected wave is equal to the magnitude reduced by this much, and then the phase of the reflected wave will be shifted by this phase angle. So we just put those values in. So it's just 63% roughly of the wave is reflected, and it's phase shifted slightly by this amount here. Likewise, the magnetic field is the same, so we have to divide by the intrinsic impedance of region 1, which we said was eta naught, which is the free space intrinsic impedance, 377 ohms. Everything else basically the same as before. And then transmitted, again, this magnitude, so a little over 40% of the wave is transmitted through the boundary. And we see that it is also phase shifted by the phase shift of the transmission coefficient. And likewise, the transmitted magnetic field is again same the same multiplier times the magnitude and the phase shift.